Hello, welcome back. Chapter 15, Part 4 on temperature. Um, you heard about the guy who froze himself to absolute zero. He's 0K now. I get it. 0 Kelvin. Not okay. Anyway, really not very difficult. This last section is more theoretical than it is anything else. Um, really, three things rather, they want you to know about temperature. First is that the collisions are translational, which means that you have that whole law of conservation of momentum thing happening where the faster particles are translating energy to the slower particles. And they want you to be able to describe that based upon kinetic theory. So, in other words, particle physics. And number two, that temperature is a macroscale phenomena. It is the average of what many particles are doing, that not all the particles are moving at the same speed, and we saw that in the first video, and that this array of particle motion is what we call the Maxwell-Boltzmann distribution, or in other words, it follows a normal curve. It follows our whole thing that we've been doing with data since the beginning of the year. And then three, as a result of the fact that not all the particles are moving at the same speed, all things are going to go through some sort of dynamic phase change where they either produce a vapor or they recondense into a liquid. And if you put them in a closed system, they'll reach a condition called dynamic equilibrium. So we'll go through all three things. Let's start with the translational collisions first. Okay. We did this when we did thermodynamics earlier in the year. So when they say use kinetic theory to describe how heat is transferred, again, remember that we have to have two objects that are in contact with each other, and that the translation of heat between one object and another occurs at the interface. And you can read this. I'm going to go through it with you anyway, but again, that collision at the interface is what's important. We also have collisions within the substance itself, spreading the heat out. But in order to transfer heat from one object to another, we really focus on the interface between the two objects. And we would describe the particle motion in the hot object as fast and the particle motion in the cold object as relatively slower. And then it's just a matter of conservation of momentum, that we are going to have the fast particles hit the slow particles and slow down, and the slow particles speed up as a result. And we would say that if we leave the two objects in contact long enough, they reach a condition of thermodynamic equilibrium, which means that they have the same temperature as each other. But that doesn't mean each individual little atom or molecule is moving at the same speed. They don't. They follow a normal distribution curve. So that's actually a review. 2, the Maxwell-Boltzmann stuff. All right, let's get to that. Maxwell-Boltzmann. Okay, so we showed in that little app with the particles moving around that not all the particles are moving at the same speed. So when we talk about temperature, it's supposed to be a measurement on a macro scale. You know, we're going to take an object which has moles of particles, trillions and trillions and trillions of particles, and we're going to say that, hey, if something has a certain temperature, we're really describing its average kinetic energy, not the energy of each particle. But we know that not all particles in a sample are going to have the same exact velocity. However, most of them reach pretty close or are pretty close to the average of each other. And this array of particle motion we call the Maxwell-Boltzmann distribution. And there's a couple of different ways of looking at this distribution. One way is to compare an object in its solid phase to its liquid and to its gas phase. So a couple things about this distribution. One, can you have some extremely moving or fast moving solid particles in a sample? And the answer, of course, is yes. I mean, if we look at this part of the graph Right here, we have some fast-moving solids. If you have a gas of that same material, can you have some extremely slow-moving gas particles in that sample? Yes, but the extremely fast-moving solid particles are rare. The extremely slow-moving gas particles are rare. Most of the particles are within one standard deviation of the norm. So when we talk about temperature for a solid, we would take a look at this part of the graph at the top peak, and we would say, well, okay, well, within one standard deviation, we know we have 2/3 of the particles are moving pretty close to this average. So our temperature really is the average. So we take a look at the maximum of the peak and following that down, and that would give us our temperature description. But can you have some extremely fast movers in a sample? Yes, even in a solid sample, you're going to have some extremely fast movers. Can you have some extremely slow movers? Sure, even in a gas, which generally we're talking about faster average velocity to get something to boil and become a gas, you can still have some extremely slow movers in there. Second thing about this graph is take a look at the range. There is a lot more variety of speeds in a gas sample for particles than there are in a solid sample. And that has to do with the fact that gases have more types of motion than liquids or solids. Second type of Maxwell-Boltzmann distribution, we could take a look at velocity of particles based upon their mass. We know that kinetic energy, just write that. Okay, that is really upsetting me. Hang on. Kinetic energy is equal to 1/2 mv squared. Okay. Well, if that's the case, then if we say that we have these four gases all at the same temperature, let's say we're at room temperature, we have a much higher average velocity for the one with the smallest mass. And again, that just goes with our kinetic energy equation. So really, when we talk about temperature, we're talking about the kinetic energy of the particles in the sample. So at a given temperature, for Ke to be the same value for all four of these substances, they're going to have different masses. So if you have a high mass, you're going to have a lower velocity, as in xenon. And we would say algebraically that this is an inverse proportion. And notice also that not only do the lighter particles like helium have a higher average speed, but they have more of a variety of speeds as well. So again, when we talk about increasing the temperature, what we're really doing is increasing the average particle velocity, but that doesn't mean every single particle is moving fast. There are always going to be some extremely slow movers in example, and some extremely fast movers in example. And again, it follows Gaussian statistics, but most of them are going to be very close to the average. All right, so the third thing is this issue of spontaneous phase change and dynamic equilibria. So, pardon me, I think I'll go through that first and then come back to this slide. Here we go. All right, so normally I would ask this as an essay question, but I'm going to have to find ways to put it in a multiple choice on this test. All right, we have a closed system. Let's say we have a bottle of water. In the sample of the liquid part of the water in the bottle, you have some extremely fast-moving liquid particles in there. Most of them are average speed. Some of them are extremely fast-moving. Some of them are extremely slow-moving, but most of them are close to the average. So when an average speed or a slow-moving particle bounces into another, they just hit each other, bounce off, nothing happens. But what if two extremely fast-moving particles hit each other? Is it possible that they could have so much energy that when they hit and bounce off, they have enough work energy to escape the liquid phase and become a gas? And the answer is yes. That's what we mean by evaporation. We have spontaneous phase change between a liquid and a gas. In the same sense, what happens in a gas sample? If we have water vapor above the liquid water, is it possible that a slow-moving water particle, not one of the average ones, not one of the faster-moving ones, but one of the slower ones in the distribution, is it possible for them to hit the surface of the liquid and not have enough energy to bounce off of that surface? And the answer is yes, and we get spontaneous condensation as a result. So in any sample of a liquid or even a solid, you have this spontaneous vaporization of particles when fast-moving particles hit each other. Now, it only occurs on the surface of the liquid, and the reason why is because further down in the liquid, you have other particles above it, and their intermolecular forces prevent the particles below it from vaporizing. But on the surface, you only have particles below you, not liquid particles above you. So when two fast movers hit, they can do enough work to be able to escape and become a gas. If we keep the container closed, eventually the rate at which things are evaporating will equal the rate at which things are condensing. Now, if we take the cap off the bottle, then what has to happen is enough of the water has to vaporize to reach an equilibrium with the whole entire Earth's atmosphere, which isn't possible, so all the water eventually evaporates out of the bottle. But all things have this what's called vapor pressure, solids and liquids, where there are some spontaneous evaporation that's occurring where particles are hitting each other and vaporizing. The volatility, they use the word volatility, describes how much has to vaporize before you reach an equilibrium condition. But this is the nature of dynamic equilibrium between phase changes here. We just have two competing phase changes that are occurring at the same time, at the same rate. So you don't see any difference on a macro level, but on a microscale level, we do have change between the liquid and the gas that's constantly occurring. All right, so what does that mean by this whole vapor pressure thing? If you have a liquid in a container and then you seal it in a system, the liquid in the container hasn't vaporized yet. As it starts to vaporize, more and more particles are leaving the liquid phase and becoming a gas. Now, how much of that vaporizes, again, depends upon the nature of the liquid. Some things evaporate very quickly, like alcohols, for instance, or acetone, where things like water, which have high intermolecular forces, do not vaporize quickly. They don't evaporate quickly. But as you start to accumulate gas particles, like in the middle diagram here, now you have a lot of particles that are entering into the gas phase. So that means that if we look at the Maxwell-Boltzmann distribution, that means we're going to have some extremely slow movers in there as well. And when those slow movers hit the surface of the liquid, they recondense. Eventually, if we leave them together long enough in a closed system, the rate of evaporation will equal the rate of the condensation, and the amount of pressure that is created by that liquid we call the vapor pressure. All right, we said another thing that we can take a look at with the Maxwell-Boltzmann distribution is that if we compare substances that are at the same temperature, then the ones that are moving the fastest on average are going to be the ones with the lower molecular mass. As we said, kinetic energy is 1/2 mv squared. So if the temperature represents the average kinetic energy, that means that if we have large masses, we have very slow velocity on average. And if we have very small masses, we have very large velocities on average. So this question on a test, which of these would have the greatest average velocity, and which of these particles would have the lowest average velocity? Again, it's going to go by molecular mass. So I'm going to work that out real quick. Actually, a pretty easy calculation. All right, so again, if we're talking about temperature means average kinetic energy. And the way they show average is they just put a bar over top of it. And in the beginning of the year when I was talking about Gaussian curves, I was talking about X bar being the average. Bar just means we have a extremely large sample of materials. So we have a large amount of particles, moles of particles, and we know that kinetic energy is 1/2 mv squared. So we said that this was an inverse relationship. If the mass is high, then the velocity is going to be low in order for it to multiply out and still get the same value for the kinetic energy. So we said carbon dioxide and oxygen and chlorine. Well, we look up their molar masses, and carbon dioxide comes out to be 44.009 grams per mole. We look up oxygen on the periodic table, we get 31.998 grams per mole. And chlorine, let me take out my calculator. 35.453 times 2, 70.906 grams per mole. And so what they'll ask you on the test is they'll say rank these according to increasing velocity or decreasing velocity. So if they ask for increasing velocity, we would say that the heaviest particle, the chlorine, is going to have less velocity than the second heaviest, carbon dioxide molecules, which has less velocity than the lighter particle, which is oxygen. And if they ask for decreasing velocity, on the multiple choice you would select the lightest particle is the fastest, and then carbon dioxide, and then the heaviest is the slowest. Alright, so please try this. Go ahead and pause it and give it a shot. If we had ammonia, helium, and methane, I want you to rank them all at, I don't know, let's make something up, 72 degrees Fahrenheit. I want to know, please rank these by increasing velocity. All right, so I'll give you a chance to look up those values on the periodic table and come back. Welcome back. So ammonia is 17.0 something. Let me say 14.000 plus 3 times 1.008. So 17.031 grams per mole. Helium is 4.002 grams per mole. So helium is going to be the fastest. And methane, 12.011 plus 4 times 1.008, I get 16.043. All right, so this is going to be my lightest, so this is going to be my fastest. And this is going to be my heaviest, so this is going to be my slowest. So if we go towards increasing velocity, we would say that ammonia has less velocity than methane, which has less velocity than helium. I know. Please put a whole bunch of these on the test because they're easy. And let's see. Temperature scales. Celsius and Fahrenheit. Okay. Notice they use degrees C and degrees F for Celsius and Fahrenheit. Degrees means compared to something else. So if you turn, for instance, 180 degrees, you're now facing the opposite direction of where you originally were. If we look at degrees and longitude and latitude on a map, again, you're comparing yourself to the equator, or you're comparing yourself to the prime meridian. So degrees always means compared to something else. And the Kelvin and Fahrenheit scale, we said in the beginning of the year, you can't use it as the SI unit because it's compared to water, and water boils and freezes at least boils, well, it's slightly different for freezing too, depending upon elevation, depending upon air pressure. So it changes as you go to different places on the planet. Water doesn't boil at 100 degrees C when you're in Denver, Colorado, where there's less air pressure. So the Kelvin scale is the scale that they use in science. And in the Kelvin scale, the lowest value you can have is 0. So 0 Kelvin we call absolute zero. It's the temperature at which particles would stop moving altogether. Now, they've never been able to duplicate absolute zero temperature in the lab. They've been able to get really, really close, and if you graph it, you can extrapolate that graph, and they estimate that all particles would stop moving at negative 273.15 degrees Celsius. They've been able to get the particles to stop vibrating. They can't get the electrons to stop spinning. Oh well. So in the temperature scale, we never have negative values, so we're going to use the first quadrant when we're dealing with temperature. So anytime we do calculations with gases like Gay-Lussac and Boyle's law and Charles' law, we're always dealing with the Kelvin scale, not Celsius. But our thermometers are in Celsius, and it's very easy to make the change. Kelvin equals degrees C plus 273. You can memorize that. It rhymes, degrees C plus 273. And the only thing I could tell you about the calculations is be careful with the sig figs. For instance, if I was to say, all right, we have 16 degrees Celsius, I want to know what is that in Kelvin. Well, Kelvin is equal to degrees C plus 273. So we could substitute that in and get 16 degrees C plus, well, I don't have to put degrees at that point, 16 plus 273, and then this, of course, comes out to be 289 Kelvin. All right, easy to do the sig figs there, but don't remember, it's the rule for addition. So you have numbers all the way down to the ones column, so you have to have a significant digit in the ones column for your final answer. Now, if you use 273.15 and you do the same problem, you get 16 plus 273.15. The answer is not 289.15. Again, this value 16 only has a sig figs in the ones column, so our final answer can only be in the ones column. So we would add this up, 289.15 Kelvin, and then we would limit our answer to what's going on in the ones column. So the answer would still be 289 K. I think that's it. We already did this, and there's a little graphic about how if you heat one side of a container, the particles are going to have a high velocity, and they're going to have to collide within the container, and then the other side of the container is cold. It takes time to translate that heat because you have to have particle collisions within the container in order for that to translate the heat across. So a lot of times, like for instance in the lab, when I'm dealing with boiling water, you'll see me come by. I'll just grab the top of the beaker where the water is not in contact with the glass, and I'll take it off the hot plate, and I can get away with doing that because I know that it takes quite a long time to transfer all the heat through the glass so that the top of the glass that's not in contact with the boiling water is hot. Notice I've never grabbed the beaker where the water is in the beaker. I would, of course, hurt myself. And that's it. We did phases of matter in video 1. So that's chapter 15. It's not really a hard chapter. A couple things for you to practice, but not really a lot of calculations. The calculations come up in the next chapter, chapter 18. So thank you very much.